Hello, students, and a very warm welcome to today's Explainer class. Today, we're diving into a really fascinating chapter in mathematics, mensuration. We are going to explore 3D shapes, figure out their surface areas, and really understand their volumes. So please settle in, pay close attention, and let's get started.
Created by Mindsticks Foundation Trust.
Here is what we are covering today. First, recalling 3D shapes. Second, spheres and hemispheres. Third, the volume experiment. And finally, some practical real-world applications.
Section 1. Recalling 3D shapes. Let's quickly refresh our memory on the 4 key figures you studied last year. First up is the cuboid, where the volume is length multiplied by breadth multiplied by height. Second, we have the cube, with a nice and simple volume of L cubed. Third is the cylinder, which has a curved surface area of 2 pi r h and a volume of pi r squared h. And fourth, the cone, where the volume is exactly 1/3 pi r squared h. It is absolutely crucial to keep these foundational formulas fresh in your minds as we move forward.
Section 2. Spheres and hemispheres.
Now take a moment to appreciate the pure mathematical symmetry of these shapes. We have a perfect sphere. Did you know that water droplets naturally form into spheres because this specific shape minimizes surface area? Nature absolutely loves geometry. It's perfectly round, much like a cricket ball. Then we have a hemisphere. This is exactly half of a sphere, shaped just like a bowl. For both of these shapes, the radius r is our master key. It's the one single measurement we need to unlock all of their secrets. Let's accurately note down their formulas. For a full complete sphere, the total surface area is 4 pi r squared, and the volume is 4/3 pi r cubed. Now imagine we slice that sphere perfectly in half to create our hemisphere. The volume becomes exactly half, bringing it right to 2/3 pi r cubed. The curved surface area is 2 pi r squared. But please remember this carefully, students. The total surface area of a solid hemisphere also includes that flat circular top, making it 3 pi r squared in total. Section 3. The volume experiment. Here is a brilliant little setup to see where these volume formulas actually come from. We are taking a solid ball and a cylindrical beaker. Crucially, they both must have the exact same radius r. Next, we cut a strip of paper with a length equal to the diameter of the beaker, meaning it has a total height of 2r. We draw 2 lines on this strip to divide it into 3 equal parts, and we stick it perfectly straight up along the inside from the bottom of the beaker. Let's walk through the physical steps of this experiment. Step 1. We fill the beaker with water exactly up to the first mark from the bottom. Step 2. We slowly push the ball down into the beaker until it touches the very bottom. And what do we observe? The water level rises exactly up to the top of the strip, which is that height of 2r. From this simple water displacement, we can logically deduce that the total volume of the ball plus the original water exactly equals the volume of a cylinder with a height of 2r. Let's gently guide ourselves through the mathematics of what just happened. The volume of the cylindrical part up to height 2r is pi r squared multiplied by h. Since our h is 2r, this gives us 2 pi r cubed. But remember, the water originally only occupied 1/3 of this height. So the volume of the ball itself is the total volume, 2 pi r cubed, minus that original water volume, which is 1/3 of 2 pi r cubed. When you solve this neat little algebraic equation, you get exactly 4/3 pi r cubed. And there you have it. That is brilliantly how we derive the formula for the volume of a sphere.
Section 4. Real-world applications.
Mathematics becomes truly powerful when we apply these concepts to solve real-world problems around us. Let's look at a very practical civic problem. Imagine a cylindrical water reservoir. It has a radius of 2.8 meters and a height of 3.5 meters. Now, if one person requires exactly 70 liters of water per day, for how many persons is the water in this fully filled tank sufficient? I want you to first think logically about how we must find the total capacity of the reservoir before we even attempt to divide it. Let's step methodically through our calculation. Step 1, we use our trusty formula for the volume of a cylinder, pi r squared h. Substituting our values, we get 22/7 multiplied by 2.8 squared multiplied by 3.5. This neatly calculates out to 86.24 cubic meters. Now, make a very special note here. We must convert cubic meters into liters. Since 1 cubic meter holds 1,000 liters, we simply multiply by 1,000 to get an 86,240 liter total capacity. Finally, we divide this large total by the 70 liters required per person, and we confidently arrive at our final answer, 1,232 persons. Just think about that for a moment.
A simple volume formula is exactly what helps an engineer or a city planner secure the daily water supply for an entire community.
Let's move on to a second real-world scenario and see how we can build upon our foundation. Suppose you've been hired to build a large circus tent. The lower part of the tent is cylindrical and the top part is conical. We need to figure out exactly how much canvas cloth is required to manufacture this entire tent. The logic here needs to be very clear. To find the canvas required, we do not need the volume at all. We only need to add up the outer curved surface areas of these two shapes. First, using the given radius and height of the cone, we use the Pythagoras theorem to find our slant height, L, which calculates perfectly to 30 meters. Then we add the curved surface area of the cylinder, which is 2 pi r capital H, to the curved surface area of the cone, which is pi r L. We can actually factor out pi r to make our final calculation much simpler. Pi r multiplied by, bracket, 2L plus L, bracket close.
Substituting our known dimensions into this factored equation gives us a final required canvas area of 4,525.71 square meters. This example perfectly reinforces how our geometric thinking translates directly into purchasing physical materials out in the real world.
Section 5, Conclusion and Homework. Now consider this complex composite toy. Observe its individual parts carefully. The base is a hemisphere, the middle section is a solid cylinder, and the top part is a pointed cone. All three are seamlessly attached together to form one single solid object. So, here is your challenge for today. When you glue these three shapes together, what exactly happens to the flat circular surfaces hidden inside the joints? Do you still count them when calculating the total surface area? I warmly encourage you to apply today's formulas and geometrical logic to solve this puzzle. Think it through, keep practicing your math, and I will see you in our next explainer class.